This is a brief summary of the study, the error analysis of numerical integrator for deep neural network modeling of differential equations. Many physical phenomena can be represented in differential equations of the form dx dt equals fx. However, the function f is sometimes unknown or insufficient, so we want to approximate it by a neural network FNN using observed data. But in most cases, we cannot get the x's, so we have to numerically integrate the FNN to compare the numerical solution with the observed data. And this discretization process causes a certain kind of error that remains even if the numerical solution matches the observed data. In this research, we have formulated the modeling error as the learnability, and conducted some experiments to examine the theoretical results. Now, let me talk about the idea of the learnability analysis. For the analysis, we use this model equation as a benchmark problem. The model equation can be considered as a linearized and diagonalized f, the function that describes a physical phenomenon. The real part of the lambda represents damping, and the imaginary part does oscillation, that roughly approximates the local behavior of the f. We can easily calculate the exact solution for each lambda, so we will use them as observed data and see what function the FNN actually learns. Especially, we analyze the case that the linear dynamics is learned as FNN. Many other functions can be learned, but this is the most preferable case in the sense that the learned model is of the same form as the target. So we define the relative difference as the learnability. If this value is small, we consider that the lambda is learned well. This is the idea of the learnability analysis. If we can calculate the learnability coefficient, we can visualize the learnable dynamics for each numerical method on lambda plane. The colored region is a region where the learnability is under some thresholds, which means that the lambda zone region is learnable. So from this example, we can say method A is better than B for learning damping dynamics, and so on. For such analysis, we have to calculate the learnability for each method and for each lambda. This is our main result, the equation that the alpha satisfies. If we use the Runge-Kutta method as a discretization method, there is an alpha whose numerical solution is exactly the same as the exact solution of the model equation lambda, and the alpha is shown to satisfy the equation. By using it, we can compute the value of alpha for each method and for each lambda, which visualize the learnable regions. These are the counterplots of learnability coefficients for some simple Runge-Kutta methods, the Euler method, the midpoint method, and the classical fourth-order method. If we allow 10% of the error, the lambdas inside the circle indicated with 0.1 is learnable. This result shows that the Euler method is not suitable for diverging dynamics, which is on the right side of the plane. In contrast, the Runge-Kutta 4 is good at such dynamics than damping one. And the midpoint method has weakness on the negative side of the real axis. So far, I've shown the theoretical results. The following is the experimental result. In this case, we used a simple multi-layer perceptron to learn the oscillating dynamics, lambda equals 1.5i with the fourth order Runge-Kutta method. As a result, learning seems to be successful, that is, the numerical solution of the FNN is on the exact solution of the target. But the learned FNN indicated as a red curve differs from the target lambda indicated as the black one. And this error is well predicted as the alpha, the blue line. As a conclusion, we defined the modeling error in learning differential equations as the learnability coefficient, and formulated the way of learnability analysis. The theoretical results are verified by the learning experiments. The most notable contribution of the study is that we proposed a new viewpoint of designing numerical methods other than the conventional ones. For a detailed description, please check out our paper. Thank you for watching.